October 27th, 1944, J. Robert Oppenheimer, director of the Los Alamos Laboratory, gives the order to begin construction at the Alamogordo test site in the New Mexico desert. If all goes well, a 10,000-pound egg-shaped bomb named Fat Man will be hoisted to the top of a tower sometime next year. A button will be pressed, a plutonium core will go supercritical, there will be a blinding flash, a mighty boom, an enormous blast wave, and America will enter the atomic age. But how did we get here? What is Fat Man, and how does an atomic bomb work? Let's look at the story so far. I'm Indy Neidell. This is a World War II in real time special on the development of the atomic bomb. There are actually two bombs under development at Los Alamos, Little Boy and Fat Man. The key difference between them is the choice of fissile materials. Those are the radioactive metals that make them go boom. Little Boy uses uranium, a naturally occurring element that has to be enriched to be used in a bomb. Fat Man uses plutonium, an artificial element that is created by bombarding uranium with neutrons. Until the summer of 1944, Oppenheimer, his boss Leslie Groves, and the other scientists at Los Alamos thought they could make two bombs that were virtually identical, save for uranium versus plutonium. But that is no longer the case, and the designs of Fat Man and Little Boy could hardly be more different. On top of that, Los Alamos are so confident in Little Boy that they aren't even going to test it, while Fat Man has caused them no end of sleepless nights. So why are these two bombs so different? First, it might be useful to have a quick reminder on nuclear fission, a concept we've covered a few times. The isotopes used in nuclear weapons are uranium-235 and plutonium-239. When these are bombarded by neutrons, the nucleus of the atom splits into two smaller nuclei. This releases a whole load of energy and also shoots out a few extra neutrons. These extra neutrons zoom around and hit other plutonium or uranium atoms, which then split into smaller nuclei and release more neutrons, which hit more atoms. In just a fraction of a second, this reaction releases enormous quantities of energy. From the late 30s, scientists like Albert Einstein and Leo Szilard had both theorized and warned that fission could be harnessed for an extraordinarily powerful bomb. Of course, things are a bit more complex than that. If you have too little material, known as a subcritical mass, the fission reaction will eventually peter out. This is because not all the neutrons that are emitted during fission will bump into another uranium or plutonium nucleus. Some of them just fly off into space. Fortunately, there is a simple solution to this. Just increase the mass of uranium or plutonium undergoing fission. If you have more material, it increases the likelihood that a neutron will hit an atom before it flies out of the system. Once you get to a certain mass, known as the critical mass, the reaction becomes self-sustaining and releases a steady amount of energy. For uranium-235, critical mass is about 50 kilos. For plutonium-239, it's about 10 kilos, but because these metals are so dense, 10 kilos of plutonium is not much bigger than a baseball. Can you imagine MLB but with radioactive baseballs? I wonder if that would be good or bad for attendance. Anyhow, the steady, controllable reactions of critical masses will be harnessed after the war in nuclear power stations. But when you're making a bomb, you want an exponential reaction which produces an enormous amount of energy in a fraction of a second before exploding. What you need is a mass greater than the critical mass, a supercritical mass. But you can't just have this pre-assembled and ready to go. I mean, this bomb needs to be built, loaded onto a plane, and carried to its target. And you sure do not want any premature detonation. So you need to keep the bomb safe and subcritical until the exact moment that you want it to explode. Los Alamos thought they solved this problem back in early 1943. In April that year, Robert Serber delivered a series of orientation lectures to the scientists. These lectures will be published as the Los Alamos Primer and will still be read by students and scientists in the 21st century. In these, Serber described the gun-type assembly method, and it's pretty simple. A gun-type bomb itself is essentially just a big metal case which holds a cannon inside. At the front of the cannon is a cylindrical subcritical piece of uranium called the target piece. At the other end, there's a subcritical tubular piece of uranium called the projectile or the mating piece. The mating piece sits on a pusher plate, behind which is a block of conventional explosives. You detonate the explosives, the pusher plate shoves the mating piece down the gun barrel, where it envelops the target piece and forms a supercritical mass. The assembly process takes less than 100 microseconds. That's 100 millionths of a second. When that happens, you get your supercritical mass, your exponential chain reaction, and your big boom. So, through 1943 and into 1944, the scientists at Los Alamos are confident they'll be able to use the gun-type method for both the uranium and plutonium bombs. The head of the Ordnance Division at Los Alamos, Navy Commander William Parsons, known as Deke, starts work on a common bomb model known as Thin Man. Thin Man weighs in at about 3,600 kilos, 8,000 pounds, and is essentially a 5.2 meter, 17-foot long tube with a bulbous nose section and a simple set of tail fins at the rear. The tube has a diameter of 58 centimeters, 23 inches. Inside is a smoothbore cannon which will launch the uranium or plutonium target piece with a muzzle velocity of almost 1,000 meters per second. By the autumn of 1943, thoughts are already turning to how to deliver Thin Man to the target. The physicist Norman Ramsey leads the delivery program, and it soon becomes clear that the only plane suitable is the B-29 Super Fortress. But there's a problem. See, standard B-29s have two bomb bays, one fore and one aft of the wings. And Thin Man is too long to fit in either one of them. The Avro Lancaster's bomb bay could accommodate Thin Man, but Hap Arnold, head of U.S. Army Air Forces, vetoes the use of a non-American plane. So, on December 1st, 1943, USAAF headquarters directs the Material Command at Wright Field in Ohio to begin a high-priority modification program codenamed Silver Plate. The first Silver Plate B-29 goes under the knife, and the engineers remove the fuselage section between the two bays, thus creating a single 10-meter-long, 33-foot bomb bay. But as we shall see, this all proves to be unnecessary because Thin Man ends up on the scrap heap. Thin Man's end comes in the summer of 1944 after Los Alamos has a serious crisis, a plutonium crisis. Okay, I need to explain a little bit more nuclear physics, just what you were hoping for. So, both plutonium and uranium undergo something called spontaneous fission. This means that sometimes the nuclei of the atoms just randomly split without being bombarded by a neutron. The risk with spontaneous fission in a gun-type bomb is that even within the 100 microseconds that it takes the gun to slam the two pieces of fissile material together and assemble a supercritical mass, spontaneous fission could cause a chain reaction to start, and the bomb could pre-detonate. This would mean the bomb consumes only a fraction of the total plutonium or uranium core, and it wouldn't reach its full explosive power, its yield. This phenomenon is known as fizzling, and it risks turning Oppenheimer's multi-million-dollar bomb into a worthless dud. For pure samples of plutonium-239 and uranium-235, this is not a problem. Over 100 microseconds, pure Pu-239 undergoes only 0.01 spontaneous fissions. In other words, there is a 99% chance the bomb will reach its full yield. The situation is even more relaxed for pure U-235. But Los Alamos' uranium and plutonium are not pure. The U-235 is contaminated with U-238, and the Pu-239 is contaminated with Pu-240. These are different isotopes of uranium and plutonium, meaning they have the same number of protons but a different number of neutrons. The U-238 is no issue, but the problem with Pu-240 is that it has a much higher rate of spontaneous fission. A Pu-239 core contaminated with just 1% Pu-240 will undergo 3 spontaneous fissions within 100 microseconds. This wasn't a problem before spring 1944 because the scientists were working with tiny samples of plutonium produced in a cyclotron at the Berkeley lab. These had a very low contamination rate and therefore a very low spontaneous fission rate. But then they started receiving large samples of plutonium from the newly established X-10 nuclear reactor in Oak Ridge, Tennessee. An Italian-born physicist named Emilio Segre begins working with these samples in April 1944. By May, Segre has discovered something very alarming. The samples are more highly contaminated with Pu-240 and have a spontaneous fission rate of 261 per gram per hour. This means that the chance of the plutonium bomb achieving full yield is only 67%. That's only 2 out of 3. And things will only get worse because the Manhattan Project will soon be switching to mass-produced plutonium from the Hanford reactor in Washington State. This will have an even greater contamination and an even lower chance of reaching full yield. At a conference on July 17th, Oppenheimer discusses the situation with James Conant, the chairman of the National Defense Research Committee, NDRC. They conclude that the gun-type method must be abandoned for the plutonium bomb. Oppenheimer's aide, John Henry Manley, sums up the seriousness of the situation. The choice was to junk the whole discovery of the chain reaction that produced plutonium and all of the investment in time and effort of the Hanford plant unless somebody could come up with a way of assembling the plutonium material into a weapon that would explode. But all is not lost. Some scientists at Los Alamos have been working on just such a method. The problem is that it's much more complicated. In his introductory lectures, Serber had sketched the outlines for an alternative bomb design. Increasing the mass of a fissile material is only one way to assemble a supercritical mass. The more efficient solution is to rapidly increase the density of your subcritical mass, forcing the atoms closer together. This means that neutrons emitted during fission are much more likely to hit a plutonium nucleus rather than flying off into space. This method of achieving supercriticality is known as implosion. The implosion needs to happen very fast, and you need to apply equal pressure over the entire surface of the sphere. If you squash too hard on the top, not enough on the bottom, well, you end up pancaking your plutonium rather than crushing it. A physicist named Seth Niedermeyer has been working on implosion since early 1943. Niedermeyer's plan was to surround a sphere of plutonium with conventional explosives and detonate all of them at once. He'd been making progress, but struggled with achieving a symmetrical implosion. That was until the arrival of the Hungarian-born physicist John von Neumann at Los Alamos in September 1943. Newman had been studying shock waves at the NDRC and brought his expertise on shaped charges. A British scientist named James Tuck then suggested modifying Newman's shaped charges idea into a system of implosion lenses. Okay, these are basically curved explosive blocks which fit around the inner sphere of plutonium. Like, imagine a ball with pentagonal rubber panels. Each block is made up of an inner and an outer layer of two different explosive materials. When detonated, explosive waves move at different speeds through the different materials and combine to create an inwardly directing, converging burn wave. Okay? This solved Niedermeyer's problem by producing a high-speed symmetrical crushing of the core. Oppenheimer gave George Kiszczewski the lead on implosion in February 1944, but up until the plutonium crisis, it was little more than a secondary backup method. This changes July 18, 1944, the day after that fateful Chicago conference. Oppenheimer writes to Groves, "At the present time, the method to which an overriding priority must be assigned is the method of implosion." With those words, the universal thin man design is dead. The implosion bomb becomes the fat man device that is set to be tested sometime next year. Let's peer a little bit into the future and take a closer look at the final design of Fat Man. The explosive part of Fat Man, which Los Alamos calls the physics package, is a giant sphere with several layers, a bit like, the structure of the Earth. It weighs about 2,400 kilos, or 5,300 pounds, which is over half of the bomb's total mass of 4,670 kilos, 10,300 pounds. At the center, you have the spherical plutonium core. This is 92 millimeters, or 3.6 inches in diameter, and it weighs about 6 kilos. The core contains something called an urchin, which is a sphere of polonium and beryllium. When the urchin is crushed during implosion, it releases neutrons to kickstart the nuclear chain reaction. The core is surrounded by a tamper, which in this case is made of uranium-238. When the plutonium core undergoes fission, the tamper reflects any escaping neutrons back into the core, boosting the chain reaction. The uranium also undergoes fission itself, which increases Fat Man's explosive yield by about 30%. The tamper is covered by a thin layer of acrylic plastic reinforced with boron. All of this is encased by a thick layer of aluminum. The aluminum transfers force uniformly from the detonation of a double layer of hexagonal explosive lenses. Each explosive layer is made up of 32 blocks. They are detonated simultaneously by an electronic firing system called the X-unit. The force from these 64 lenses crushes the plutonium core to double its original density. The physics package is held in a thick steel case which sits inside Fat Man's thick, egg-shaped outer casing. After drop tests with dummy bombs, a large cube-like tail fin known as a California parachute is added to stabilize Fat Man's descent. But hold on a second. If spontaneous fission wasn't an issue with uranium, and we know that Thin Man would have worked, why bother with a new design for a uranium bomb? Why do we need Little Boy? Well, now that the gun-type bomb only needs to work with uranium, it can be simplified. Little Boy is 7 feet shorter than Thin Man, coming in at just 3 meters long. That's 10 feet long. It is 71 centimeters in diameter, 28 inches, and weighs about 4,400 kilos, or 9,700 pounds. 1,000 kilos of that, nearly a quarter, comes from Little Boy's gun, which is shorter than Thin Man's. Just 2 meters long, with a bore diameter of 16.5 centimeters, which is 6.5 inches. This is because it doesn't need as high a muzzle velocity, just 300 meters per second compared to 1,000 meters per second before, as I said. At the rear of the gun is the tubular projectile piece of uranium, which weighs 25 kilos and contains 4 urchins. At the front end of the gun barrel, we have the target piece, which weighs 39 kilos. The target piece is surrounded by a tamper of very dense tungsten carbide. Just like with Fat Man, the tamper's job is to reflect neutrons back into the system. And because it is so dense, the tamper slows down the explosion of the uranium by microseconds. Even that tiny delay allows the chain reaction to go on slightly longer and boosts the power of the bomb. As Los Alamos works on the bombs, the Air Force prepares for their top-secret mission. For security reasons, Arnold and Groves have decided that a new self-contained unit must be set up. After extensive screening and interviews, they put Lieutenant Colonel Paul Tibbets in charge. He learns of his new mission September 1st, 1944, and takes command of the new 509th Composite Group based at Wendover Army Airfield, Utah. The first 17 Silver Plate B-29s arrive there in October, and test flights begin the same month. Crews train with concrete-filled dummy bombs and learn to carry out an unusual post-drop maneuver that puts as much distance between their bomber and the atomic blast as possible. Remember I talked about the first B-29 having some pretty radical surgery to convert its 2 bomb bays into one? Well, that is no longer necessary because Little Boy and Fat Man are so much shorter than Thin Man. But these aircraft will get some extensive modifications next spring. There's an additional seat for a weaponeer who is charged with monitoring the electronic circuits of the bomb during the flight. The planes will be fitted with improved bomb release mechanisms, fuel-injected engines, and variable pitch propellers. All defensive turrets will be removed, except for the tail guns, and the Silver Plate B-29s will be 3,300 kilos lighter than normal B-29s. And that brings us to where we are now. Oak Ridge Laboratory will soon be churning out enough U-235 the Groves orders all research and development on Little Boy to be completed by July 1st, 1945. Los Alamos has tested almost all of the individual components, and the design of the gun-type bomb is so simple that Groves and Oppenheimer believe a test is unnecessary. It would only consume precious uranium. But they are less certain of Fat Man's implosion technology. When Fat Man's test might happen is contingent on the production of plutonium. Hanford is up and running, but it's still up in the air whether they'll be able to produce fast enough. But as we come to the end of the year, James Conant of the NDRC is more optimistic about the development of Fat Man. He gives a 50-50 chance of the bomb being test ready by May 1st, 1945, and a 75% chance by July 1st. We shall have to wait and see if they get the job done. Astrid made a Spies and Ties episode all about Klaus Fuchs, a Los Alamos physicist who leaked loads of information about Fat Man to the Soviet Union. If you would like to watch that, and you really should, you can click right here. And to get ever more content like this, join the Time Ghost Army at timeghost.tv or patreon.com. See you next time.